We can extend our understanding of motion by adding one more variable into the mix, the concept of acceleration. And we'll just toss this right out for you right away. Average acceleration is equal to the change in velocity over change in time. So this is kind of a natural offshoot of velocity, which is a change in position. Acceleration is a change in velocity. So that's v final minus v initial over some final time minus some initial time. And we can figure out the units, and sometimes I'll use this shorthand notation. When I put something in brackets, that means I'm talking about the units of them. So that's going to be the units of velocity, whatever those are, divided by the units of time. So to figure out the units of acceleration, that's going to be velocity, which was meters per second, divided by seconds. So we can simplify these to meters over seconds squared. That is going to be our units of acceleration. Now velocity, that was a vector, so that means acceleration, also a vector. So it has magnitude and it has direction. Don't get confused with this concept of something called deceleration. We're not going to use that word in this class. Deceleration can be confusing. It can kind of be weird. We are going to denote if something's decelerating using the vector notation, vector concept. So if something's decelerating, it's traveling in the negative direction. Acceleration is negative. Okay. Now we also have, in addition to this average acceleration, similar to velocity, we have instantaneous acceleration. And the instantaneous acceleration, a of t, is equal to derivative of velocity as a function of time with respect to time. Okay. So we can think about this also as a slope on a graph. So this is slope on a velocity versus time graph. So we can see this, we can see all of this. This all kind of comes naturally from our understanding of velocity. Now, in physics, there's something called constant acceleration motion. And this is a big key to lots of basic physics problems and basic physics concepts that we need to understand. We need to understand constant acceleration motion. So this means that the acceleration is not changing. It's a distinct number. Okay, and these equations that we're about to show you, they're derived in the book, and these are ridiculously important. I cannot emphasize how much you have to know these. Just friggin' memorize them. Okay? So we have an equation for position. X equals x naught plus average velocity times a time. We also have an equation for velocity. Average velocity equals v initial plus v final, and we'll just leave the f off to imply that it's still final, divided by 2. So that is my average velocity. And then now come the real key equations. These are the big dogs. These are really what you really want to know, and you'll be using these constantly. So if you're doing your homework properly, you're not going to be able to help but memorize these. We have some velocity, some final velocity. V is equal to v naught plus acceleration times a change in time. We have x is equal to x naught plus v naught times t plus 1/2 a times t squared. And we can sometimes also write this as change in x is equal to v naught times the change in time plus 1/2 a times change in t squared. And then finally, the last kinematic equation that we want to know, v final squared equals v initial squared plus 2 times a times x minus x naught. And if we want to write this in delta notations, we can do that, where we have v squared equals v initial squared plus 2 times a times delta x. Okay, so these equations I'm going to circle in red. If you make note cards, this is a great thing to make note cards of. These are the 3 kinematic equations. Memorize these. Okay. So these all apply to motion with constant acceleration. One of the most common constant acceleration motion equations or problems we'll have are acceleration due to gravity. Gravity has a very specific value. It's a constant value. It's equal to g. We use the letter g to denote it, and it's equal to basically 9.8 meters per second squared on the surface of Earth if we take the magnitude. Now, if we account for the direction, usually gravity pulls things down, right? And we're going to assume in this class, when I do problems at least, I'm going to use the convention that anything down is negative. So g is always going to be equal to negative 9.8 meters per second squared when we're using it in kinematic motion. So let's do a quick example. Let's say I take a ball and I throw a ball in the air. Okay, so I throw a ball straight up. So it's going to go up and it's going to come back down. I catch it after 10 seconds. And I'm going to ask a bunch of questions about this. I'm going to ask, what is the acceleration? So how fast is this thing accelerating throughout the whole path? It's going to be a constant acceleration motion. Let's figure out what that acceleration is. I also want to know, what's the initial velocity? What's the velocity I threw this ball up at? I want to know, what is the velocity at the peak when it reaches its highest point? I want to know, what are t, but basically what is t at the peak height? How long does it take for this to get up to its highest point? And then finally, I want to know, what is v when I catch it after 10 seconds? So there's a lot of stuff here. There's a lot of stuff we need to know. How do I do this kind of problem? Well, first I draw a picture. So here I am standing here. I'm very skinny. And I'm going to take a ball and I'm going to throw the ball up. I take a red ball. I'm going to throw it up in the air. It's going to reach some peak height. It's going to stop and it's going to come right back down. And I'm going to catch it at the exact place that I caught, that it left my hand. I know that this total time that this is going to take is equal to 10 seconds. So how do I start solving this? How do I start finding these things? Well, my recommendation for every kind of kinematic problem, make a chart. So after you make a picture, so that's the first step. The second step is to make a chart. And in that chart, you want to include every kinematic variable. You want to include change in y. What's the change in position? You want to include the initial velocity. You want to include the final velocity. You want to include the acceleration. You want to include the change in time. You want to include all these variables. And then you want to write down, what do you know about this? The change in y, the total change in position. What is the total change in position of this thing? Well, again, that's the change in position. That's the total displacement. So I go up, I hit some peak, and then I come right back down to where I started. So the change in position, that's just going to be 0. The initial velocity, don't know how fast I threw it up. The final velocity, we actually don't know what this is. This is a subtle thing that happens in physics problems. It can be somewhat confusing. When I talk about final velocity, I mean right before I catch it. Okay? It has to do with when I catch it, I'm exerting a force on it, so that changes kind of the rules. But right before I catch it, that's the final velocity that we're talking about. Acceleration, what's the acceleration? Well, the only thing acting on this is gravity. Gravity's pulling it down. Gravity has an acceleration g equals negative 9.8 meters per second squared. You should go ahead and memorize that number too. Chant it as you go to bed. A is negative 9.8 meters per second squared for acceleration due to gravity. And then the change of time is going to be 10 seconds. Okay, so we have our nice little chart. Now we need to start figuring out some variables. We need to start figuring out some things. For part A, what is the acceleration? Well, it's in our chart. It's negative 9.8 meters per second squared. Done. That question was easy. Part B, what is the initial velocity? Well, I don't know what V naught is, but I have all these kinematic equations. I have all these great equations I can use. Can I use change in x equals V naught times change in t plus 1/2 times a delta t squared? Can I use that? So to figure out if I can use it, I look at all the variables. Do I know what change in x is? No, but I know change in y. And these these change equations are interchangeable. So change in position x, we can just as easily say that that's change in y. That's a change in position. So we can use these horizontally or vertically. So I do know change in y. I know that variable. V naught, that's what I'm looking for. Okay. Change in time I know is 10 seconds. I know the number 1/2. I know the acceleration. I know the change in time. So I can just plug and chug into this equation. Now, what I recommend doing, instead of immediately plugging in your numbers, do some algebra here. Do some algebra on these letters. If you practice algebra on letters, you get better at doing it on numbers, and you will be doing a lot of algebra in this class. Okay, so I need to get my V naught by itself. To do that, I can first follow some steps. Let's do these steps. I can subtract 1/2 a delta t squared from both sides. So I get change in y minus 1/2 times a times change in t squared is equal to V naught times change in t. If I want to get V naught by itself, I divide both sides by a change in time. And my change in time cancels out on the right-hand side, and I divide the left-hand side by that change in time. So now I know what my V is. My V naught is equal to the change in y minus 1/2 a times change in t squared, all divided by change in t. You can plug in all your numbers here. Plug in the numbers. Change in y is equal to 0 minus 1/2 times a, which is negative 9.8, times change in t, 10 squared, all divided by the change in time, which is also 10. V naught, when you plug in all of these numbers, you'll find is equal to 49 meters per second. So there we found our initial velocity. Next question. We want to know what is the velocity at the peak. So velocity at the peak. Well, if I'm throwing this ball up, it goes up, it reaches the peak, it stops, and then it comes back down. If I've stopped, then I'm not moving. If I'm not moving, V equals 0. V at the peak is equal to 0. Done. Okay, what's part D? Part D, we were asked, let's scroll up, time at the peak. How long does it take this ball to reach the peak height? So change in y, do I know what that? Oh, I don't know what that is. I don't know how high the ball goes up to the peak. V initial, I now know what the initial velocity is. I know I threw this ball up at 49 meters per second. V final, what's the final velocity of this ball? At the peak, it's equal to 0 meters per second because it stops and reverses direction. The acceleration is negative 9.8 meters per second squared. And the time, do I know what the time is? I do if I think about physics, but we're going to assume for now that I don't know the time, and we're going to see if we can calculate it based on these variables that we know. I look at my kinematic equations. Let's start with the first one. V equals V naught plus A times change in T. Can I use this equation? Do I know V? I know V. Do I know V naught? I know V naught. Do I know A? I know A. The only thing I don't know is T. So I can find what the change in time is. I can find how long it takes this to reach the peak. So I'm going to do some algebra on this again. I subtract my V naught from both sides to get that this is equal to A times change in time, and then I divide both sides by A to get the change in T by itself. We need to get very good at doing this kind of algebra. Practice it. Do it constantly. Okay, so change in time is the velocity divided by the acceleration. So change in time is equal to V final, which was 0, minus V naught, which was 49 meters per second, all divided by the acceleration, which was negative 9.8 meters over second squared. Plug all these numbers in, you'll find your change in time is equal to 5 seconds. That kind of makes sense, right? The total time is 10, so to get to the peak is half of that total time. And the last question we were asked in part E was, what is the final velocity? So this is the final velocity after the whole path that I've traveled. So my change in y now, it goes back to 0, right? I went up and I came back down. My initial velocity, still 49 meters per second. My final velocity, and again, this is the velocity right before the ball hits my hand, that's what I'm looking for. My acceleration is negative 9.8 meters per second squared, and my change in time is equal to 10 seconds. So we can pick pretty much any equation we want. Let's look at the first kinematic equation, v equals v naught plus a times change in t. Will that actually work for us? I'm looking for v final. Okay, so I don't know what that is. I know what v naught is, I know a, and I know t. So I can just plug and chuck. V equals v naught. And notice I don't know I have to do any algebra on this to get it in the right format. Plus acceleration is negative 9.8 times the change in time, which is 10. So I can plug all these numbers in, and when you do that, you'll find your velocity is negative 49 meters per second. And this is interesting. It's the same magnitude as my initial velocity. Right? The sizes are the same, but the position, the direction has changed. Okay, and that makes sense because initially my ball is going up, and at the end my ball is coming down. So the velocity directions have simply reversed.